The title is Public Key Cryptographic Implementation Validation Present and Future. And it will be presented, and the authors are Dr. Anand Mohan, Dr. Abhay Jacob, and Ragvendra Patil. So I think the paper will be presented by Mr. Ragvendra Patil. Yeah. So I invite presenter.
Uh, uh, Hello, thank you, Deepak. I'm Ragvendra Patil. Joining me online is Dr. P.V. Anand Mohan, and this is we are the three authors. So this is basically public key cryptographic implementation, validation, present and future. So the work is done under the MIghty project funding. So the agenda is basically we'll discuss about the validation requirements for cryptographic implementations, then the public key standards for both RSA digital signature algorithm as well as the elliptic digital signature algorithm, and the we'll see the NIST shortlisted post-quantum cryptographic algorithms and how we can test them, and the final conclusion. So basically, the two more widely used public key algorithms are RSA and the elliptic curve, and they are extensively used even in PKI environment. So these are useful for authentication and digital signature, and even for the key exchange mechanisms. So digital signature, as we know, the first hashing of the message is done using SHA-1, SHA-2, and latest with SHA-3 algorithm, any of the algorithms. So this implementation can be either in hardware, firmware, or software. The basically the validation concerns with the correctness of the algorithm rather than the implementation of the algorithms. So there are two types of the basically, if you look into the FIPS 140/2, there are two kinds of testing and validation. One is a CAUP, other one is a CMAP. The CAUP concerns with the algorithm validation, and the CMAP concerns with the module validation. So basically, the prerequisites for the CMAP is CAUP. That is, the algorithms you have implemented either on the hardware or software or in the firmware, they have to be certified first. Then you will go for a module validation based on the certain security criteria. So how it happens is, initially vendor has to sign a MOU with the lab. Then he has to upload his security policy. Then the lab will send a certain request files for the checking the algorithm validations. Once the algorithm validation is passed, then the certificate will be issued. Then we'll proceed with the module validation. For a module validation, you have 11 requirements. So particularly, specification, module specification, interfaces, specification of the interfaces, roles, services, authentication. Like that, you have related to operational security and the finite state machine and the mitigation of other attacks. Say if you have implemented any side channel attacks and all, that can also be tested. So this is according to FIPS 140/2. Now they are updated to upgraded to FIPS 140/3, and the it is aligned with the ISO 19790. So you have some not an extra, mitigation of the other attacks was optional, say in the FIPS 140/2, now which is made a mandatory in 140/3 and the ISO 19790. So now, for example, no, this presentation or the paper mainly concerns with the public key cryptographic validation. But since AES used everywhere, so if we take the example test done on the AES has a basically block size of length 128 bit, which is, and you have a key size varying from 128, 192, and 256 bit. So once if you have implemented an AES, once you will be given with a certain test from the lab, like GFS box, key S box. GFS box is for the operation of AES algorithm. Key S box is for the testing the S box implementation in the key schedule. So you have variable text and variable key, and suppose you have these are for the single message block. Suppose then you since in the practical it will be used in the multi messages will be used. A message can be as long as can be very long. So you have a multi-block message tests also, and Monte Carlo test for the finding out the any errors in the implementation, say memory leaks or the you would have allocated a memory and may not have freed it. Such things will be found out from the Monte Carlo test for different modes. Now they have introduced the authenticated modes of encryption also, like CCM and GCM. Though tests for those modes are also available. So basically, since we had many discussion on the post-quantum scenario, in the post-quantum scenario, AES 128 bit will become vulnerable due to Grover's algorithm, but 256 will be still very strong. So we need not worry about the AES with respect to the in the post-quantum scenario. Only we have to increase the size of the key. So now coming back to the RSA, so RSA is widely used in the digital signature and key exchange mechanism also. So usually the suggested is earlier suggested one was 1024 bit, but NIST now currently suggests 2048 or 4096 bits. So all operations are done on integers. So basically the RSA, the security of the RSA depends on the two primes generated of equal size P and Q, which are the private, and the product N is made up public. Okay, so and basically, you just can't construct any primes. The primes constructed have to be strong, and you just can't do with the whatever explained in the textbook or the examples. So there are certain restrictions. You have to check for the strong primes, and the particularly if you are going for a encryption or the signature RSA signature thing and all, you have to follow certain padding mechanism so that certain attacks on RSA can be avoided. So these are the NIST tests on RSA. So the key pair generation and validation. There are three types of RSA test. One is a key pair generation and validation. Other one is a signature generation, and the last one is a signature verification. With respect to key pair generation and validation, so as I have explained, RSA key consists of primarily two primes equal size in equal size P and Q. So they can be generated using a provable prime method, probable prime method, and provable with conditions based on auxiliary provable primes. So basically what it says is you have something called a provable prime. A provable prime means you don't generate a random number, then you try to prove it. For that you have a AKS method, which is a polynomial in time, and other methods, but they are not still practically not feasible. So what we do here is in provable prime method, you construct here the construction of the prime is done. Basically you take the smaller primes, then you under certain conditions you construct a prime where you can prove that it is a prime. You don't run a provable prime test on that, but rather the construction ensures that it is a prime. So that is a provable prime method using a it's based on the Pocklington lemma. Yeah. So and there are probable prime method where you use a Miller-Robbins method and Lucas method and all. And there is something called then you have a RSA signature generation and verification, which are based. There are three standards basically: ANS X931 and PKCS version 1.5 and PSS. So using these three standards, you will be able to, we have to follow the further generation of RSA signature and verification. So these are the different tests for the key pair generation. So validation test is you have two types. One is for provable primes and the primes with condition. In that case, what 25 sets of the test vectors will be set for each of the different primes you are generating, and the tester has to generate those primes and has to return it to the lab. Lab will validate whether they are correct or not. With respect to probable primes, you have two tests. One is a known answer test. Other one is a keygen random probable test. In case of KAT, so the lab will generate the primes and the public key exponent E and other related parameters, and will ask the vendor to test whether they are correct or not. And in keygen random test, lab requests the vendor to send a 10 pairs for each of the primes he is going to generate, and for each of the modulus with respect to the RSA modulus, and the lab will validate whether they are correct or not. So these are the key pair generation tests. With respect to signature generation thing, lab will send a 10 sets of the messages. The vendor has to respond with the different E, P, Q, and message, hash of the message, and the signature. Lab will test whether they are correct or not. Similarly, for a verification, what lab will do, lab will generate a different kind of signatures, RSA parameters, and will send it to the vendor. Vendor has to, some of the things will be intentionally modified for a wrong signatures. So the lab has to, the vendor has to check which of the signatures are correct, which of the signatures are wrong, and has to send back the result. So this is a RSA thing. So with respect to the ECC thing, it can be over the prime integer field or the binary field, and can be over the Publc curves also. So with respect to integer primes, you have P192, P224, P256, and P521. So the one speciality of these NIST curves is that they have a simplified structure, in the sense P192 can be represented as 2 raised to 192 minus 2 raised to 64 minus 1. So if you see the exponent of this, you can see this is the multiple of 32-bit. So this leads to the optimization. You can optimize your implementation, and you can simplify the representation of P192 curve as T plus S1 plus S2 plus S3 mod P. So which will which will result in the faster modulo implementation of faster modulo operations. So similarly, compared to the RSA, you have 4 basic steps: key pair generation, public key validation, signature generation, and signature verification on ECDSA. So if you take the elliptic curve definitions, so you have this is one example elliptic curve. So you have prime modulus P and the order of NP, order of NPs. So N of P should give the point at infinity. And you have 160-bit input seed to the SHA-1 algorithm, and the output C of the SHA-1 algorithm, and base point GXGY. Okay, I'll just finish. So basically, coming back to the so you have a generation in the signature generation. So key pair generation test, same thing. Basically lab will send ask you the DUT to send the sum of over the curve, whatever he has selected. Ask him to send the sum of the keys, and it will test whether they are correct or not. Signature generation test, lab will generate the the lab will ask the vendor to send the signatures, and it will check for the correctness of the signature. Verification, lab will send the some six signature for each pair of the a public or a private key exponent, and it will intentionally modify the signature, and the vendor has to find out whether they are correct or not. So similarly, for the we have something called earlier SHA-1, SHA-2 were there. Now we have come up with the SHA-3. NIST has come up with the SHA-3. So that is based on the sponge construction. You can see that here you have a short message, selected long message, pseudo random, Monte Carlo test, and the variable output test. So basically, as others discussed, NIST has come up with the round 3 winners. They have shortlisted 4 algorithms, 1 KEM, crystal, Kyber, and the 3 digital signature algorithms. So they have 4 alternatives for the next round. One is already broken. So I'm concluding. So the point I'm trying to make is whatever the textbook algorithms you have studied, that may not be enough for implementation. So you have to do a rigorous testing to achieve the objectives. So the future is NIST has upgraded to FIPS 140/3, and you have ISO 19790 and the ISO 24579 and ISO 18367. These standards have to be followed for a validation of the algorithms. Thank you.